Hello everyone, welcome to this webinar. It's top of the hour. Let's get started. Today's webinar is sponsored by RavenDB, the company behind the NoSQL document NoSQL database, and InfoQ. My name is Srini Penchikala. I serve as the lead editor for the AI/ML and data engineering community at InfoQ. I will be the moderator for this webinar. Today we're going to hear from Oren Eini from RavenDB team. The presentation title is Deep Dive into the Architecture of an Indexing Engine. So a very interesting topic. So let me introduce our presenter first. Oren is the founder and CEO of RavenDB with over 20 years of software development experience. He is an internationally acclaimed presenter, a thought leader, and an author committed to continue and lead innovation of quality software and best practices. So a quick background on today's topic. With the ever-increasing data that we need to manage, the indexing and search engines play an important role in the database platforms. RavenDB is a document NoSQL database platform that supports transactional ACID features and end-to-end solutions for efficient data management. So in this webinar, Oren will discuss the architecture of their new search engine called Corax, and we'll also show us some data examples on how they build this solution to meet their performance goals. So before we go to the main presentation, I would like to go over a couple of housekeeping items. The main presentation will be about 30 minutes to 35 minutes long. After that, we will have a 15 to 20 minutes Q&A session where the presenter will respond to questions from you all. I will be moderating the Q&A throughout the presentation. If you have any questions during the talk, please post them in the questions tab in the GoToWebinar control panel. We also have a few poll questions today that Oren will be sharing during the presentation. Please take a few seconds to respond to these questions. It really helps us understand where you are in your NoSQL database adoption journey, and also what to focus on, especially when we follow up with you after the webinar. Everyone's microphones will be muted by default except the speakers. The recording of this webinar will be available in the next couple of days for you to watch it offline, either if you missed the webinar or if you want to re-watch it after the webinar. So that should be all for housekeeping items now. Oren, I'm going to turn it over to you, and I will turn off my video. Very much looking forward to the presentation. Please go ahead.
Hi, thank you very much, and thank you for having me. Today I'm going to be talking about an indexing engine, which leads to a very interesting question. What is that? So the easiest way is to ask Google, which is also an indexing engine. So that's good. So we know that the indexing engine allows me to index probably data, but that's the boring part. The interesting part is that it allows me to actually ask questions on that. If you look at the question you ask Google, you can answer pretty much everything. When you talk about how it actually is built, we're going to drop from, oh, this is Google, all the way down to how it actually works. In here, you can see some sample queries. And if you think about it, when you execute a query on Google, on your systems, eventually it ends up being something as simple as this. And you know what? Google is a multi-trillion-dollar company. That seems like a really complex thing. So how do you even approach that? So I thought about this really hard, and eventually I came up with this idea. This is an indexing engine. It's written in Python. It fits in a single slide, which I'm very happy about. And I want to go over this for just a little bit to understand what's going on. We have this state that is basically a dictionary of a dictionary that's contained in the set. Really complex stuff. And what we do is, okay, we add a term such as here, a title for document number 1, and the title is indexing engine. And if you call a term, what we're going to say is, okay, give me the dictionary of terms for title, split the terms, and store it here. And that's about it. And we do the same thing for everything in here. The end result is this data structure, which you can see here, the field terms. And it's really interesting because there is a field for title. And inside that, there are all of those various terms, engine, indexing, search, etc. So this is a term. In this case, you can see great is a term of the field status. And then we have something that is called a posted list. Let's go back one step and understand what's going on. When we call add term, what are we doing? We are first splitting all of the terms, lowering them, and adding them to the right posted list. Adding it to here. For example, we have awesome. How did awesome 1.2 get here? Well, let's look. Here is for document number 1, status awesome. So we run it here and we add it. Same thing for document number 3. Why is this important? It is important because when we go the other way around, when we want to do a search, what do? We say, oh, here is for particular field, for particular query. Okay, let's split a query, lower it, and search it in here. And that's it. This is an indexing engine, this is a query engine, and now we can start actually applying that on the real world. Let's see. Here we have some questions. So give me all of the documents whose title contain indexing and the status contain awesome. How do I do that? Well, let's go to title, let's go to engine, and let's go to indexing, which contains just one. This is the posting list, so you can see it right here. And let's look at status is awesome, which is 1 and 3. I can intersect both of those, and this is the result. I found all of the documents that has full text search title in their index and have the field awesome. We're good. You can see the exact same concept, or it's just a union and end note exclusion, and we're done. This is the overall concept of take the data, throw it into this sort of data structure, and then you're done. Now, on top of that, you can start building really complex things. But this is the basic, this is what you need to understand. Of particular importance is, notice this is the posting list. Posting list is the list of all of the documents that match a particular term. So all of the documents that have the term status is awesome is in here. And the terms are basically, we took the initial text that we index, we broke it apart into individual words, individual terms. And this is where we end up. There is a huge amount of additional complexity. How do you break the text that you want to index into terms? How do you do things efficiently? I'm not touching that right now. I just wanted you to have some concept about what an indexing engine is. So let's talk a little bit more. I've been working on RavenDB for about 15 years now. It is a document database that uses JSON. And from day one, we were using Lucene, which is a search engine library. So we were able to do full text search, and it was amazing. And it is a really, really good library. Lucene is the industry standard for searching for a reason. Unfortunately, the more time goes by, the more I have to squeeze out of the hardware that I get. I need to be faster and faster because you guys keep giving me greater and greater challenges, which is amazing because I don't know if this is noticeable. I love what I do. So I want you all to meet Corax, and Corax has one specific purpose. It is meant to be fast and do everything that Lucene can do, but so much faster. So with this, let's see how we are doing. So Corax is something that we've worked on for just under 3 years. We have been designing a replacement for Lucene in our system for about 8. This is a really tough challenge. The nice thing about this is that in the top, you can see an index inside of RavenDB that is executing, and we just created this index and we're now running that. it is executed at a rate of 27,000 documents per second. The same index under the same hardware and the same environment is executed at a rate of 156,000 operations per second. That's wow. And we can actually do better. This is a pretty complex index. So think about just look, 8 minutes versus 1 minute. This is an amazing difference. And it is very easy to show that when we talk about indexing times. But let's dig a little bit deeper and see how we're actually doing that. Because Lucene is not a Python indexing engine with the code that fits in the slide. It's a big mature project that people work on for decades. So let's talk about what we're trying to achieve. We want to be faster, we want to be speedier, but it's actually turned out that this is a multi-dimensional problem, because what am I talking about with speed? I can trade off indexing speed for querying speed. What about I can trade off speed for space, time for space, but which space? On disk, in memory. I can make most things a lot faster at the cost of every now and again I'm hitting this big cost that I have to deal with. So for Corax, the design principles went like this. I want to be order of magnitude faster in indexing and in querying. I'm willing to pay for that because, again, it's all about trade-offs. I'm willing to pay for that in additional disk space usage to a reasonable limit, obviously. And I must always have a constant cost. So I should be maintaining those invariants of being so much faster and without, oh, every now and again I have to do this really expensive operation. And the reason for those things is that all of those things have been really painful for us over the years. Those are the pain points that we're trying to avoid when building a new system. So Corax is really, really, really good. When I'm saying that, I mean that it is really good. I think it got started in the early 2000s, so it's now 25 years old, something like that. And it has been the industry standard across a wide variety of environments for a really good reason. It is really good. But we cannot use that because we outgrew what it can offer. So let's see how we write our own. Before we do that, then this is specifically for raising the tension, there is a poll going on, and I would really appreciate if you answer that so we can learn more about what you feel is important in the realm of database and database management. Okay, so the way that we deal with performance optimization for Corax is to use trees, because B trees are pretty amazing thing. I try to find out when we first discover, utilize B trees, B plus trees. The earliest mention that I found is before 1970. And even then it was just, oh yeah, everyone is using that. It is ubiquitously used, which is amazing, but still kind of small. Because I want to know who the first person who thought about that and shake his hand. That's an amazing algorithm. And RavenDB in general and Corax specifically use B-trees for everything. So B-tree, if you're familiar with Data Structure 101 or 601, whatever that would be, is basically a way to structure the data in a way that makes sense for storing it in a persistent format. From a modeling perspective, this looks like a dictionary where the key is a string and the value is some long. Key for our purposes is that we customize everything about this B-tree. The dictionary is not a dictionary, the keys are not keys, and everything. So the goal of everything is to get high density of value. What does it matter? We are dealing with large data sets, hundreds of gigabytes, multiple terabytes, and we need to be able to index and search on those very efficiently. In order to do that, we typically don't get machines with terabytes of memory. We have to be able to squeeze the index data structure in as little memory as possible, which also help overall performance. So we have done a lot of work on compression. At the same time, one of the design principles for Corax is that the data is ready-made. That means I don't need to read some compressed data from this, unpack it, decode it, and then work with that. I should be able to work directly on the compressed data. So let's see how that works. There is an algorithm called HOP, high-speed order preserving encoder. And it is a really, really interesting algorithm because this is a compression algorithm that uses a dictionary. So far, this is nothing special. The really interesting about it is that it is order preserving. So I can take all of the common items that I have, and you can see that users repeats a lot. And I can generate a dictionary that would allow me to compress that. Instead of 5 characters, I can store that in 1. It's actually in bits, but we won't touch on that. And why does it matter? It matters because if I'm compressing that, would I still be able to compare 2 values, or would I have to decompress them, compare them to find which one is greater? And finding which one is greater is an operation in databases that happen billions of times a second. So this needs to be super, super fast. By having an algorithm that allows me to generate the compressed data, it has the same order as the decompressed data, that gives me a lot of power. Because now I can just sort the compressed data directly. This is amazing. This saves a lot of disk space, a lot of computation. Because now even your comparison are working on this data. So here is a compact tree in Corax. And I want to go over what's going on for a little bit. Here you can see this is the root. And here are some leaf pages. Those are fairly standard things for databases, B++. Where does it get interesting? Notice that we are not storing the keys inside the B tree. We are storing that outside. There's just a reference to the B tree, which means that I only need to store inside the pages of the B tree just the references. The key itself is a reference to some other location, which is in 64. The value is always in 64, and that's it. I can pack thousands of them into a single B tree. It's a single B tree page. More to the point, that means that in terms of a horizontal density, I have a huge amount of that. It takes me millions of entries to go into the next level of the B tree. And again, that means that I can index over a vast amount of data using very little amount of memory. So the whole concept here is to effectively allow me to search, given this term, give me the appropriate value. But what is this value? This is the posting list ID. So let's talk about a posting list for a second. A posting list is the list of document ID that match a particular term. So the compact tree from before is going to be for a particular field and the values thereof. For example, here is the compact tree for the status field. Give me the posting list for awesome. That's how it works. Now, it turns out that in practice, we have 3 types of posting list. We have a single posting list that contains 1 item. This is very common if you have a GUID, a date, which is millisecond precision or nanosecond precision, etc. Tends to be unique. You have a unique value from somewhere, email, etc. Then you have the value that has a few items, maybe a few hundreds, few thousands, but no more than that. And for example, the number of orders for a particular customer ID. And then you have posting lists which cover a huge amount of data. Give me all of the orders who start, the posting list for the orders whose status is shipped. Most of them are. So here's what we're doing. Remember that the value that we store in the compact tree is a 64-bit int. And we ensure that the entry ID that we're searching is always a multiple of 4, which means that we can pack additional information into the actual value. So if this is a single list item, the last 2 bits are empty and I can use it immediately and directly. Otherwise, this is a small item or a large item. And let's talk about what's the difference between those two. A small posting list is just a buffer, a small buffer. A large posting list is another bit tree. I love trees, if you remember that. And let's see how it actually works. We're using something called fast PFor as the algorithm to store the posting structure. It's something called patch frame of reference, and we touch exactly how it works in a bit. The key aspect of it is a very efficient compression data for numerical data. So it goes through this algorithm. You force sort the data, delta encode, just subtract one from the other, find the number of bits that you want, pack them, and handle the exception. This is probably went right over your head. It looks simple, but let's see what's going on. Here are the numbers that we want to encode. So the first thing that I'm going to do, I'm going to sort them. Notice that 861 dropped to the bottom. Now I'm going to delta encode those. What does it mean to delta encode? I'm dropping this as a first, and then this minus this minus this, etc. And now I need to find the frame of reference. What is the frame of reference? How many bytes do I need? I'm using here bytes, but in practice this is bits. How many bytes do I need to efficiently encode that? And you can see that I can encode most of those values in just 2 bytes. This one, I cannot. But this is why I have the notion of patch. I'm encoding all of them using 2 bytes and record that I need to record this one and I need to add another one. Here is one such item. This is the original term that we have, and this is in 64, so it takes 8 bytes. Here you go. This is what happened when we encode this using bytes. So this is the base number, the delta for the fourth, second, third, fourth. And now, hey, you need to patch with this value. So I can get this working. And when using bits, I can typically get ridiculous rate of compression ratio. To give you some context, 56 kilobytes of longs, I can pack them into 4 kilobytes. That's a lot of longs. That's thousands and thousands that I can pack into just 4 kilobytes. And the way that I'm doing that is super, super, super ugly. You can see here, I have literally a file with tens of thousands of lines of code. And also not normal lines of code. This is actually using vector instructions to emit super specific bit packing instructions that allow me to do this sort of compression or encoding, however you want to call it, in a super efficient manner. The end result is that this is really, really fast. So this is based on work by Lemire and Boncz, and they are able to decode things at billions of integers per second. They're actually using int32. I'm using int64. It's a little bit more complex, but it's good because I don't actually need to process billions. Why don't I need to process billions? Why am I limiting myself? I want to process billions. Well, it turns out that remember, one of the constraints that we have is that we need to be able to run online manner. All operations have a constant cost. I cannot have, oh, now I have to decode 10 gigabytes of data and pack it with this other 10 gigabytes of data to summarize things. By the way, this is something real that Lucene may need to do because of its design. And this is something that we explicitly did not want to do. So because we assume that we are online and not batching operations, then we have this concept. A small posting list, remember, this fits up to thousands, tens of thousands, I think it's something like 7,000 longs inside, compressed into 4 kilobytes. This is a small posting list, which is just a buffer. The large posting list is a bit tree where every leaf page is an 8 kilobyte buffer of compressed numbers. And again, really, really high density. The bit tree also allows me to do skipping and seeking into a list of compressed values that may be hundreds of thousands of millions of items inside. So here's how it goes. The posting lists are sorted. So what's the cost of adding and removing to a posting list that has 5,000 items? Well, it is a small posting list because it can fit into 4 kilobytes. And I want you to note how fast we can do that. The ugly code that I showed you earlier is really, really fast. It turns out that it is cheaper to decode, merge two sorted lists, and encode the data again than do anything else. We're actually faster than using memcopy. And just look at those numbers. Almost 45,000 items, 360 kilobyte. I can get ridiculous level of compression. I can do that really fast. 400 million items per second to encode, 1 billion items per second to decode. And I'm always doing that on bounded values, either 4 kilobyte or 8 kilobyte if I'm using the large posting list. In the case of the large posting list, I'm not modifying the entire list, just that particular buffer inside the page that I'm working on. In fact, if I have a large posting list, then I would typically always add items to the end, which means that I'm only touching one buffer, and this becomes really, really efficient. This was actually a real surprise to me, because when we started, we tried to be smart about it and not decode and encode all over again. Turns out this is so much faster. We don't need to worry about it. And removing the optimization makes things faster. Now, we have an indexing engine. We have a posting list. Everything is cool. Now we want to run a query. I'm going to show you an amazingly complex query. Behold. Take a moment to appreciate that. The model that we have here is Stack Overflow. So we pull the data from the Stack Overflow data dump, load that into RavenDB, and now we're running a question. It doesn't look like a really complicated question until you realize, hey, JavaScript and PHP are both super popular values. How am I going to run this? Well, I'm going to go to the tags field. Give me the posting list for JavaScript. Give me the posting list for PHP. All them together and give me the force 15. We're good. Oh, wait, we forgot the order by. The order by is a killer, because if you think about it for 1 second, this is really, really fast. I can do that very quickly. But when I would be able to just give you here the force 15 and I'm done. Cheap and easy. Where does it get interesting? It gets interesting when I need to order by, because now I have to go through 3.6 million results. That's expensive. I mean, think about what it actually is required. First of all, I have to sort 3.6 million results, cost of n times log n. But before that, I have to go and fetch the creation date of 3.6 million results. That means that I have to go and, okay, give me the date for this, give me the date for this, give me the date for this. What happens if they're on the disk? I'm going to start hammering the disk using effectively random IO. That's a killer. I cannot run that. So what can I do? I want to show you the costs. Here we are running this query. This is the first time empty machine, so you have to pay the entire cost. This is using Corax. As you can see, we are not happy with this. Even though this is an expensive query, etc., it costs us almost a quarter of a second to execute this. Same exact query, but now using Lucene. First time that we run this query costs us over 7 seconds. This is actually a really good example of the reason we wanted to move away from Lucene. Because the design of Lucene make a lot of assumptions. Oh, I want to save a lot of disk space and I defer a lot of work to runtime. Or I'm going to work in a batch-oriented manner. Or I'm going to do a lot of work when I'm reading things and building in-memory caches, etc. All of those things that we do not allow in Corax, leading to even the force query being so much faster than Lucene. But this is not fair. Let's compare what happened if we run it a few times. And you can see that Lucene in this case is actually much improved. But so does Corax. And Corax is almost twice as much in this particular scenario. And it turns out that the reason we can be faster is that we are applying different optimizations to this process. So take a look here. Here is the JavaScript posting list. And I want to sort by creation date. What I would have to do, I would have to basically, okay, give me the creation date for post number 11, for 32, for 13, and then do all of that. If I have a small number of results, for example, if I search for Lua, that is a perfectly fine operation to do. But what happens if I'm talking about something like JavaScript, which has a million operations? Well, I don't want to do random IO over a million items. So I'm going to go the other way around. I'm going to say, hey, I'm going to scan through the index and try to say, hey, do I have any matches for the first value? Do I have any matches for the second value, etc.? Why does it matter? If I have a lot of value, there is a strong likelihood that I would match it very quickly. Even if not, I still gain just by the fact that I'm able to operate better in terms of overall IO. Because as I'm scanning through the creation date index, I'm using sequential operations versus random operation when I'm doing that. And this has been my attempt to go into very complicated topic very, very quickly and give you some ideas about how we're able to build a much better indexing engine, both in terms of indexing and querying time, as well as our ability to fit that into the overall architecture and feeling that we're trying to get from RavenDB, where throw the data in, run your queries, we will take care of everything else. You don't need to learn about the 6 million various option configurations that you need to do to make things faster. And with that, I would love your questions. I think you're muted.
Oh, sorry. Thanks, Oren.
Yeah,
thank you so much. Thank you so much for an excellent presentation. Very important topic and very timely topic. Audience, please post your questions in the questions tab in the GoToWebinar control panel. We have time for Q&A. So let me start. With a couple of questions on my side. Oren. So how does the RavenDB indexing engine differs from other NoSQL databases? Other document database. How do they do this?
So let me try to show you. And I'm going now to the public instance of RavenDB. Feel free to go there as well. And what I want to look at is, let's go and create a new system. And okay, this creates a sample data. And now I can go into this index. Well, okay. I want an interesting one, so this would be good. Okay. So here's the index, and those are the terms that I index in this index. So for orders, here you have the employee, the company, etc. Now, the interesting thing about it is I can now ask all sorts of really interesting questions on this particular index. Let's go and run and see what sort of question I can. So I can ask a question such as, give me all the items for a particular company. Or I can now ask, give me everything for a particular employee. Now, if you look into this, this doesn't look impressive. I'm just running the query. Here's where it gets really, really interesting. If you compare that to an index in SQL Server, for example, you would realize suddenly that, hey, this is weird because I'm indexing now on company and employee. Okay, but I can also use the same index to query over employee, where the total is greater than some value. This is not something you can do in a typical index in a relational database because the set of fields dictates so much about what you're doing. If you're indexing multiple fields, then that's the nature of how you have to query that from now on. With RavenDB, what we're asking you to do is tell me the fields that you want. And I'm now in charge of figuring out how to make it execute efficiently, properly. You don't have to deal with all of those permutations and everything. So that gives you a lot more flexibility. Another really important aspect is how we deal with the unexpected scenario. So what I'm going to do right now, I'm going to delete all of the indexes from the system, and I'm going to go ahead and issue a query. And I get some results back. And now you can see that I suddenly have an index. This is an index that's created by RavenDB automatically, transparently, based on us. And this is not something that created. This is something that RavenDB created based on my behavior. I would now go and look at another query, again on employees. Last name equal Fuller. And here is the result. And I have two indexes. One is by first name, and one is by first name and last name. But that's a waste. So RavenDB reacted to my queries, created the appropriate indexes, and now I have just one index. And the reason I have one index is that RavenDB is smart enough to say, hey, I created this index initially, and then I have another field to index on the same collection. But because the indexes in RavenDB do not require you to specify the order, it's not meaningful, we handle it eternally, then I can just add that field to a new index and remove the old index. Over time, I'm running in over time, I'm able to issue all of my queries, and RavenDB is going to end up with the set of optimized indexes that I need in order to run without me needing to manually specify everything and keep everything up to date.
Yeah, thanks for an excellent explanation how it works. So yeah, let's go through some of the questions from the audience. Peter has an observation and a question. So the observation is, when you shared the poll, the first poll, you just talked about speed just before that slide. So he's kind of suggesting that that might have influenced the audience to pick speed. Speed came back with 45% response, right? So yeah, that's a good observation. But anyway, also on that poll, I see 0% of the audience. I mean, none of them picked a cheap or free option. They don't have to pay for it. So I'm really happy about it because as a community, we want to make sure that we are getting the value out of these solutions. Not necessarily we are not paying anything for these, right? So always the cost should align with the value, right? So I'm glad they didn't pick that. So it should be the least of our concerns. So let the cost be the chief executive officer, chief finance officer concern, right? For us it should be reliability, peace of mind, and of course speed, right? So okay. So yeah, Peter does have a question. So the question is, how does Corax FTS speed compare with other engines such as Postgres and MySQL? Yeah, you just mentioned that, right? But do you have any like a Postgres type of comparison specifically?
I don't believe that we have done a Postgres full text search versus RavenDB full text search, mostly because even if you're using full text search in Postgres, this is of typically limited value. You can use that; it gives you some value, but by saying, okay, if I don't have sophisticated needs in full text search, I can still use this. But full text search in Postgres means that it's quite expensive in terms of computation. The amount of queries that you can write, the queries that you write are more complex, etc. You typically can see the benchmarks to Lucene, Postgres to Lucene, which I know there are benchmarks for that, and you can see the numbers of Lucene versus RavenDB, Lucene versus Corax in RavenDB, which is basically just ridiculous.
Yeah, excellent. Thank you. Next question is from Cresto. Question is there any risk in switching from Lucene to Corax on production database? I don't know if the question is more of a dynamic migration or just in general.
So you can. So let me show you how we do that. Let's go pick a database that has some index, and this index is currently using Lucene. I'm actually going to do a bunch of. Where is it? This is. Okay, so now I paused indexing on this database. Oh, come on, I need another database. Is this the one? Yes. Okay. So I'm pausing indexing on these things so I would be able to show things without things happening too fast. So what is happening right now, this is an index using Lucene. I'm going to switch it to using Corax. And now you can see something really interesting. What's going on? I actually have two versions of this index that is running in parallel. What happened is that RavenDB is going to go ahead and index this. This one is still active, running, processing, whatever. Once this is done running, RavenDB, this is called side-by-side indexing, and then we're going to basically refresh that and switch this one for this one atomically. I can go here and enable indexing, and I will be able to see that this is now a course index. So in terms of operation, you can actually replace that on the fly. Now, again, if you're talking about small data sets, go ahead and do that. If you're talking about large data sets, we have to go over the entire collection or collections in order to do that. That's expensive in terms of I/O computation time, etc. So you can schedule during off hours or something like that. Most of everything is supported in Corax, and we support running Corax for production. There are some features that are not there. For example, phrase queries is something that didn't make the cut for the 6.0 release, and we are now working on adding that in the 6.1 release. But for the vast majority of cases, those are super edge cases that you would run into.
Thanks, Oren. Another question from Peter. How much additional storage do indexes end up requiring? So yeah, what is the, I know the example you showed, it was kind of fast in terms of performance,
Yeah.
but in terms of storage, what is the addition, overhead?
So right now, this is, by the way, you can see, this is how you can see RavenDB running on a small database. And you can see here's the data file. Sorry, let me go here and here. This data file, here is the index. You can see what the cost of that is. Most of the index, by the way, is going to be empty because we pre-allocate data from the file system in order to improve performance. But the basic idea is that we found that for the most part, Corax is within the same order of magnitude. So a Lucene index would be 2 GB, Corax would be 2 GB to 100, 2 GB and a half, something like that. So roughly the same thing. If you go down to the details, we take about 10 to 15% more, but because of allocation strategies, you typically don't actually see that. Another aspect that is really important is why we're taking more disk space. And this is because the way that we are working is about the, where is that? Here we go. It's because of this. We very explicitly made a determination that we're going to take more disk space in favor of using less memory, because disk space tends to be a lot cheaper than memory. And that means that, oh, I've done all the work, now I can just use that. There is another aspect here that is very important. If I do more work on the disk instead of in memory, that means that when I'm reading data from the disk, I don't need to do computation in order to unpack or build in-memory data structures.
Thanks, Oren. So also I'm looking at the poll questions. I think we have a couple more to share with the audience. So do you want to do that real quick and then come back to Q&A?
Yeah, absolutely.
So we do have time, right? So, okay. Let's go ahead and post the second poll. Everyone, please take a couple of seconds to address this one. This is the question: how much of your work is dealing directly with databases? So we want to know, like, how directly are you involved with the database management in your company? Okay. Okay, 50% all the time. So I don't know, Oren, do you have any comments on this poll results?
Yeah, it's really funny to see that. One of the things that is interesting is that you need a database for everything. One of the things that I was asked is, what do you need the database for? And I keep saying, yeah, everything. In the same way that I need a pen to in a bank or in a insurance company, or just to go to the grocery store. And you cannot live without databases everywhere today. And that's really interesting. It's also even more interesting when you realize that the impact it has on your day-to-day life as a developer. Oh, I need some data, or the classiest thing is, oh, I need to add a field to my system. Is it a 3-week struggle with bureaucracy and migration or something, or is it something to just do? Oh, I need to change this query. Is it going to kill us in production because I forgot to apply this index or not? At the end of the day, one of the reason that I built RavenDB and the reason it even exists is about frustration, about, okay, I need to do something and I have so many steps ahead of me just before I can start doing the real thing. And the whole point of RavenDB is, let me take it on myself to handle all of these minutiae, all of those details. Now, I personally find databases and database engines to be fascinating, one of the purest forms of working with computer science, or both because of what you're achieving, or both because this is real measurable impact on performance, on quality of life for developers and everything. But as someone, I want to build a shopping cart. The intricacies of bit-tree layout on the disk probably don't matter. In fact, actively harmful if you have to take that into account. So you shouldn't have. And that's I think is a really good result for the poll, that you still see people, oh, I'm there all the time.
Right. Yeah, definitely. Yeah, you're right. So database is probably the most important asset in the IT solutions, right? So okay. So we have one more poll. So let's go ahead and launch that one as well. The last poll. So the question is, what is the biggest problem you run into with databases in any of your projects? So this is a good question to kind of to ask at this point of the webinar, because we can follow up with you offline and based on what are your challenges. So please go ahead and take a few seconds to kind of respond to this poll. Okay, the results are out. Yeah, Oren, I don't know if you have any comments on this one as well. So looks like missing indexes and resulting poor performance is the kind of the poor modeling leading to it. Oh, I think RavenDB can address both of those problems.
I'm sorry. I'm laughing here because because it's true, because this is painful, which is ridiculous. This is supposed to be a solved problem. And one of the things that endlessly frustrated me, I show you the example before of RavenDB and automatic indexes. And this is a feature that we had since 2010. So that's almost from the very start of RavenDB. But this is not something that you generally see in most other databases, because, oh yeah, there is a DBA to do that. We imagine there is an expert handling that. And that fits into the theme of, okay, I now need to do something with the database. I'm afraid to do that. So you layer and layer and layer, because everyone tries to escape the inherent complexity. And then I used to be a database performance consultant. I would go to people and companies and customers and make their system more performant. And some cases, it was 3 or 4 orders of magnitude faster. Not because I'm very smart, not because I know too much, because I sat down and I said, okay, let's remove 6 layers of indirection in the middle. And instead of calling the database in a loop, put the call just a little bit higher and grab everything together. And those sort of things basically teach you, don't do that. It's not possible to do that. You're not sufficiently expert to do this. And it is really sad. One of the things that I set out to do is get to the point where users write a code and the database manage the things for them without them needing to understand all of those details.
Yeah, makes sense. Okay. A couple more questions. Is there any significant limitation one would encounter if using Corax or Lucene for a specific advanced query option? Corax is definitely faster than Lucene, right? I don't know if there are any other limitations.
Yeah, it is much, much faster. Not that I can think of right now. There are some specific scenarios. We expose in our API a Lucene call. So obviously, if you use that, you have to use the Lucene thingy, the Lucene indexing engine. Beyond that, there are, for pretty much any scenario, you're expected to be able to use either one of those. I mentioned the phrase query, which is something that we currently don't do in Corax, and this is an upcoming feature. Beyond that, I can't think of anything else. The nice thing about it, both of them can live in the same environment, so even if there is a problem, you can just use the other indexing engine as well.
Okay, sounds good. Yeah, thanks, Oren. So there were some other questions, but they were already answered online, so I think we're good with those. So we have a few minutes left. So do you have any concluding remarks or any comments before we wrap up the webinar?
I started thinking about Corax in 2014. I actually found the original tweet where I spiked it for the first time. And it took us a huge amount of time and effort to build it. And I'm actually happy because during that time, we also improved RavenDB significantly, and the end architecture that we have for Corax is frankly something that I found really, really beautiful. Even when you have, code file of tens of thousands of lines of code. It's also really interesting because we're able to fit that into our existing product without really, you select Corax and then you're done. You don't need much beyond this. If you're using RavenDB, I would encourage you to go and try Corax. It is really amazing. And I spent a lot of time working over those details to make sure that you will have a really good experience there. If you're not using RavenDB, I would love to have you start to get your grip, because I think that one of the things that we offer here is the ability to get it out of your hair, basically. Take all of the details about databases and management and working on those and just, okay, this is handled.
Yeah, definitely. I think try it out for your use case and see how it works. One quick question. I think Corax is definitely a core component of the RavenDB now. So do you see something similar being a standard for document databases in the future, like a faster indexing engine?
Indexing engines, okay, that is a hard question to answer, because a relational database tends to have to follow a template. They have SQL, they have certain structure, etc. Non-relational databases, document database tends to be very different from one another. If I'm comparing RavenDB to Couchbase, for example, both of them have the concept of queries and indexing, but they are vastly different from one another. We ran some benchmark with Couchbase, and they fell down at 200, 250 queries per second. RavenDB was able to process 15,000. This is with Lucene, not with Corax, so we can probably spend a lot more now. But and the reason I'm saying that is that RavenDB is meant to be a primary system of record, as well as the system where you run your OLTP workload. So queries, transactions, ACID transactions, those sorts of things. Other databases tends to focus on other aspects. Couchbase on, I want to be a really fast key value store with some queries sometimes. And that matters. If I'm looking at something like DynamoDB, which is another document database, the way that queries work there is completely different. So this is a very, very hard question to answer, because we're not even trying to compare apples to oranges, but comparing apples to camels.
Right. Yeah, they're so different from each other, right? So yeah, okay. Yeah. Sounds good. Thanks, Oren. Yeah, this has been a very informative session, and I hope it was the same for all the attendees. I want to thank again everybody who has attended this webinar, and also for submitting your questions. I think this is the first webinar, where the whole Q&A session was all hands-on. It was great to kind of see you kind of go back to the portal and show the actual indexing and switching dynamically from Lucene to Corax, and so it was a great Q&A session.
Okay, awesome. Thank you.
Thanks, Oren. Yep, thank you. Thanks, everybody. We will wrap up with that. Thank you, and we will see you next time. Thank you.
Bye-bye.
Bye.